Many thanks to the organizers for the invitation to come and the opportunity to talk. Many thanks to you for coming. This is joint work with Heiko Dietrich from Monash University. We have a preprint on the archive. I'm also grateful to NSF, which has been supporting this in part. So the problem I want to solve is a problem for finitely presented groups. If you have a finitely presented group here, typically what you know is just a very small part. And one of the main techniques for working with these groups is to try to find something larger. You know already this quotient H of the group G. You want to find a larger quotient A. And the tool for doing this is what is called a quotient algorithm. So abstractly, we have a finitely presented group G. We want to find quotients of this group because that's what we can hopefully use to test membership in subgroups or find properties of find subgroups and then study subgroups. So we take a specified class of groups. We assume we have already a homomorphism from the group to an image in this class, and we want to find a new homomorphism. So we have a homomorphism to that group. We want to find a new homomorphism with a larger image, and we want this new image is in the class. We want that the kernel of the new homomorphism lies in the kernel of the old homomorphism, and we want that the quotient of these two kernels is elementary abelian in a pre-specified characteristic P. So we want to have our new quotient will be extension by a module. Why do I care only about modules? Because I could assume that anything non-solvable is in the radical factor of the quotient I end up with, and I will assume that I have this radical factor already. So how can one do this? Well, we can ask Isaac Newton. And he, since he was master of the mint, he tells us on coins, use what other people have done before. And what has been before is a sequence of algorithms for groups. There is first the p-quotient algorithm. This starts with a paper of MacDonald in '74, then a paper of Havas and Newman a few years later, and then about 20 years after that, a paper of Newman and O'Brien, which in some way settled the p-quotient algorithm for, well, at least for the time being. So there the quotients are p groups. Then there are algorithms where the quotients are solvable groups. So there is a paper by Pleskin and a paper by Niemeyer, which use somewhat different approaches and propose algorithms where they just assume the factor group is solvable, and they find again a solvable group, and there are generalizations of this to polycyclic groups. So what I want is, however, where my group is not solvable and not polycyclic. So I want to start with the group H. It might not be with a known quotient H. I don't require that it is simple, but in particular, it is not solvable. And I will assume that this has been obtained through different techniques. So what I want to do is to follow what the p-quotient algorithm does, not what the solvable quotient algorithms do, because that ends up a bit too complicated. So let's look briefly, what does the p-quotient algorithm do? The assumption there is we work in the class of finite p groups. We have a quotient, and we want to find a new quotient which is larger, where the nilpotency class is one larger. And there one can actually define the largest such quotient, and that's what is called the p-cover. So let's assume we have a quotient, and we look at it as a quotient of a free group, modulo some relations. What we can do is we can define the p-cover, which is the quotient modulo this normal subgroup. So we factor out something to make the quotient central and p-th powers to make it p elementary abelian. We calculate this P cover, and what the P quotient algorithm does in a very simplistic form is to construct this P cover, evaluate the relators in the P cover, and then the quotient, so we have our existing group, the finite presented group, the quotient H. We calculate, we look at it as a quotient of F, calculate the P cover, and then the largest possible quotient of G, which is a P group of nilpotency class 1 larger, would be this group A, which we obtain by just evaluating the relators of G in this P cover. And that works very well and has been successfully used for decades. There are three things which come into this which make it work. And basically, these are three things which we'll have to generalize. The first is P groups have a fixed rank, a fixed minimum number of generating sets. That's Burnside spaces theorem. That's not true in general. P groups have only one module, simple module, the trivial module. Other groups have other modules. And finally, we can work in this P cover because we can represent it as a group by a polycyclic presentation, which allows us to work effectively in this group. So these are three ingredients which I will have to somewhat generalize. So let's look at trying to generalize this whole process. So again, we have a finite group H, quotient of a finitely presented group G. I lift that quotient to the underlying free group. Let's take the kernel of that homomorphism. I choose a prime P. I want the largest P elementary abelian quotient of this kernel. Well, that's basically almost the same definition as before. I put in commutators and a pth power, and I can then look at a homomorphism from the free group onto this cover, the cover modulo this kernel. If you look at how does it differ from the P cover, the only thing where it differs is that here I'm putting in not the free group as before. That was there to make it central, but now I only make it abelian and so allow arbitrary modules. Well, by the same argument as for the P quotient, if there is a larger quotient of G which still maps onto H and where the kernel is P elementary abelian, that map must factor through this cover. So the module I put underneath is the quotient of what is sometimes called the representation module, M, which depends on the factor, the prime, and the number of generators. This is this M modulo K. And here I have the number of generators which goes in implicitly. Okay, so what can we tell about this representation module? Luckily, there is a paper by Gaschuetz, which is already quite old. It's from 1954, where he describes the structure of this module and the structure of the extension by H basically in full detail. So what he shows is the structure of this module depends only on the factor group, the prime, and the number of generators. It does not depend on the homomorphism, how I'm mapping onto H. In particular, the composition factors of this module are the same as the E-1-fold regular module, direct sum with a trivial module. So if the prime does not divide the characteristic of H, we know exactly what it is. Furthermore, this module is a direct sum of two parts, where one part gives a universal split extension, and the other part is something non-split, and one can even tell how these parts split into projective indecomposables, where these are the projective indecomposables of H, all of them, and if we know the radical of the principal block, we can calculate what B is. Okay. I will briefly show you how we can construct an extension by this whole cover. That's not what I want to use in the end, because this is large. I mean, here you have the regular module a couple of times in there, so this will end up very quickly as a very large group, which is unfeasibly large. But it will be a tool towards working there. And of course, here I have the rank in some way comes in here by having to specify the number of generators. Okay, so let's first briefly look at how can I construct this representation module. So I start by taking cyclic group of order P. I could also do this for the integers to take all primes together, but then I get into then the representation theory becomes more complicated. And I'm forming a wreath product. A wreath product of this cyclic group with the factor group I know, which is of course just the semi-direct, the regular wreath product. That's just the semi-direct product of the group with its regular module. If you wonder why I'm doing this, well, I like wreath products, and wreath products are generic things where extensions embed into. Okay, I will now write this regular module additively. So next, I'm defining a set of homomorphisms from the free group into this wreath product, one homomorphism for each of the generators. Namely, what I'm doing is the ith homomorphism on the jth generator on the free group. If I is not equal to j, I'm just mapping into the complement part into h. But if I is equal to j, I'm furthermore, the part here, I'm mapping to the element which is the unit vector supported with whose support is just on the identity. Writing the regular module additively. Okay. So I get E, if I have E generators, I get E homomorphisms. I take their direct product, and that direct product goes from the free group to the E-fold direct product of this wreath product with itself. And because it's defined on a free group, it is a homomorphism. If on a free group defined on the generators, it is clearly a homomorphism. Well, then one can show, I won't bore you by going through the details, which are not hard, but are just orgies of indices. First, it's not hard to see the original projection factors through that map. Yes, because here the original projection is part of it. The kernel, what I'm putting underneath, comes from an E-fold copy of the regular module, so it's still P elementary abelian. So my kernel is correct. Then, and that is just inspection, these maps theta I, if I restrict them to the module, they are just what is called, sometimes called Fox derivatives. If you don't know what Fox derivatives are, we won't need them later. But basically, that means we can almost copy a proof for Fox derivatives. And from that, it follows that the kernel is exactly what we want. So the image of the module of the kernel under this homomorphism would be the module. The image of the free group would be this cover. So that's how we could construct it. But again, this becomes unhandily large. So I need to make some radical steps to reduce the problem. And the reduction I'm going to do is to say, I don't want to put underneath an arbitrary module. I want to put underneath a semi-simple homogeneous module. So I want that the module is a direct sum of irreducible modules of only one type. So I'm specifying a module type. Again, in the P quotient, I didn't have to do so because there is only one type of simple module. In general, there are multiple, so I'm specifying one type of simple module. And if I want such kernels, I'm not taking the whole representation module, but I'm only going in the radical factor of this representation module. So what I define is H hat VE. This is the largest quotient where what I put underneath is element is semi-simple homogeneous, where the direct summand is of type V, where V is a simple H module. Okay. Now this will be a quotient of H hat, so I get a projection also from the free group onto this. And by the same argument as for the P quotient, or as I've given you before, the maximal lift with a V homogeneous kernel would be by evaluating the relators for G in this new cover H hat VE. Note, if we have a P group, if H is a P group of rank E and V is the trivial module, this H hat VE is just the P cover. So we are really generalizing the concept of a P cover, and I think this is the correct generalization of the P cover to non-P groups. So what remains is only to actually construct that P cover. So that's what I want to show you next. So for the structure of this group, we show, and this is again something which is not obvious, which one needs to prove, this new cover, it's a subdirect product, and it's a subdirect product of multiple, well, it's a product anyhow, it has to have multiple parts. One of them is a universal split extension. You might remember that I cited from Gaschuetz that this representation module was a direct sum of two parts, a universal split part and a non-split part. That's where this comes from. With extensions which are non-split, and these non-split extensions I form for a basis of the two cohomology group. So my cover is a subdirect product of a universal split extension with such extensions which are non-split. Okay, and the important thing, and I think that is what makes it work better than the approach of the Pleskin SQ, which looks at constructs extensions and constructs all possible extensions, is we do not need to form every extension up to isomorphism or up to equivalence. We only need to form extensions for a basis of the two cohomology group. So if the two cohomology gets larger, it's still just a basis. It's not the whole two cohomology group. And the reason for this is because we have a universal split part there. So what is the proof of this? Probably a picture is easiest. If we take two extensions which correspond to cocycles and we form their subdirect product, then, and if you want, that is the theorem that the cocycles form a group, I can find a normal subgroup and form another quotient which will be an extension for the sum of the two cocycles. So if I have a basis of the two cohomology group, I can do arithmetic on the cocycles and basically for an arbitrary quotient which corresponds to an arbitrary cocycle, subtract off the basis vectors often enough till I end something which is in the co-boundaries, and then I have a split extension. And so all the extra bits are in some way covered by this split extension, and I will show you that this split extension I can construct in a nice way without having to go to extension theory. Okay, so I need to show you how I construct this split part. I need to tell you how I'm forming these extensions. So first, the split part. So for the split part, remember, V is a simple module. I'm looking at something which is in the quotient of the regular module, and I know I can calculate a priori how often V will occur as a quotient of the regular module. It will occur R times, where R is the dimension of an absolute irreducible constituent of V. I'm always working over the field with P elements. So it could be that V is irreducible, but not absolutely irreducible. So this statement, this is basically Wedderburn's theorem and a little bit more for dealing with the field extension. Okay, so that's where this R comes from. Now I'm constructing, and again, this is a theorem we prove in our paper. It's not immediately obvious, but I hope it doesn't come over as completely weird. So I want to take the homomorphism I've constructed before for the whole cover, this map into the wreath product. And what I'm doing is I'm replacing the regular module by the R-fold direct sum of V with itself. So that's the only thing which changes. And I'm taking the composition of this, so I'm factoring out from the regular module this V to the R. I'm extending this to the map onto H hat, and that gives me a new map I call theta VE, and this image I call S, and we prove that image is the universal split extension, the universal split lift, any quotient of my cover H hat that has a V homogeneous kernel and is split will factor through this map. So that's the universal split part. Yeah, that is not every non-split extension, and I need to prove something, because if I intersect, this is part of the E-fold wreath product, but if I intersect this with a cover, I don't get everything here. So there is something more complicated happening with the module, and that's the reason why this theorem really needs a proof. So how can I construct this explicitly? Here I just say I have the composition with a natural map. What I'm going to do is I really just modify the theta I have before. The regular module is a cyclic module. I take the identity element and that, or the vector corresponding to the identity element and its images. So the quotient V to the R is a cyclic module. I take, R was the maximal, the dimension of absolute irreducible summand. I take a generator Z which is a cyclic generator for V to the R. Okay, and now I define a homomorphism, theta I prime, which modifies the previous theta I, where I'm saying where that part is 0, it's just 0. Where something non-zero happened, here I had the identity. Before I had the vector 1, which was a generator of the cyclic module. I take this vector Z, the generator as a cyclic module. Then if I form the direct product of these maps, that has the same kernel, so I can use that map, that direct product of these maps, in place of this theta VE. How do I find such a cyclic generator without writing V to the R as a quotient of the regular module? What I'm going to do is I take R vectors in V whose images in an absolute irreducible quotient form a basis of this absolute irreducible quotient. And now I have R copies, and I take the vector which is the vector x1 in the first copy plus the vector x2 in the second copy plus the vector x3 in the third copy. So that's some kind of diagonal object, and we show that works. Okay, so that's the split part. For the non-split part, I said I need extensions for 2 cohomology, so I need to be able to calculate a 2 cohomology group. So That is something which in some way is not new. So there are, for example, a sequence of papers of Derek Holt from the mid-1980s when I was still in high school, where he describes how one can calculate the two cohomology group. There also is a number of papers by Jack Schmidt which use a slightly different approach using rewriting. Basically, we generalize this. There also, I should mention, though this was never formally published, was a thesis in Halle, a Diplomarbeit in Halle in the mid-90s, and I don't remember the name. Klaus reminded me that this was a student of Stroth who described this, how one can calculate the two cohomology group given a confluent rewriting system. So our only achievement, if any, is that we wrote it up in a place which hopefully will be published formally, because Schmidt just mentions that he does it but doesn't write it up in detail. So we take a finite group H, this is our quotient. We take a simple module V. We assume that we have a confluent monoid rewriting system for H. What is a confluent rewriting system? That's just a set of rules. Replace this word in the generators by this word of the generators. If you look at the first example of a group in an abstract algebra book, it's often the dihedral group, and they talk about a generator R and a generator S, and hooray, we have RS is SR inverse, and therefore we can bring elements in a normal form. What they implicitly use is that it is a confluent rewriting system. So we modify this rewriting system by adding further generators for the module. We use a wreath product ordering. Wreath product ordering here just means is to bring elements in a more normal form. If we have a module element by times something which represents the factor group, we want to bring it into this form, and the wreath product ordering just ensures that this will be larger than this. We add relations which describe what V itself is. Well, that's easy. It's P elementary abelian, and which describe the action of H on V. We change the rewriting rules for the factor by adding tails to them, where the tail is a variable, something in the module. And now we apply the confluence conditions. The confluence conditions are overlaps of the left-hand side of the rules reduced. If you have two rules whose left-hand sides can overlap, you can have something you can reduce with the one rule or the other rule, and the image needs to be the same. We are doing this, and there is a theorem, that's the Knuth-Bendix algorithm, which says that if they all reduce in the same way, the system is confluent. You have normal forms. It describes a monoid in the way, and actually in this case a group, in the way as we expect it. So we do the same, but now we have the variables in there, and that gives us linear equations in the variables. Well, we can solve a system of linear equations in variables. That gives us the co-cycles, the co-boundaries. A basis for them is easily computed, so that gives us the two cohomology group. And if we substitute a solution for the variables in these rewriting rules, we get a presentation for the extension. I'm adding here just a simple module, a single simple module, so the number of variables is not that large. I don't need something like vector enumeration, which potentially on the way constructs more something like the regular module before things collapse again. So compared with a Niemeyer SQ, this is much easier to do than before. Okay, where do we get a confluent rewriting system? And in some way, this is already written up in a paper by Jack Schmidt in 2010. So we can build it along a composition series just from the simple factors. That's the same idea how a PC presentation is put together from presentations for cyclic groups. We have conjugation rules, which bring into a normal form. The rules of the factor get tails, which describe extension structure. So what do we do with the simple groups? AN is easy. If the group has a Bn pair and groups of Lie type have, and for some sporadics we can basically find subgroups which look very close to a Bn pair. We can take a PC presentation for the Borel, a rewriting system for the Weil group, which in some way is very similar to the ones for AN or SN, because the Weil groups typically are closely related. Well, they're Coxeter groups. And we take rules for the double cosets. That's part of the Bn pairs, that every element lies either in the Borel subgroup or in such a double coset indexed by the Weil group. And so we can transform. There will be rules which we can calculate in the group, that if we have Weil, Borel, Weil, we can transform to Borel, Weil, Borel. And they, if we use a suitable ordering, they will give us a confluent rewriting system. This is, I didn't get the code from Jack Schmidt, so I re-implemented it. It's not yet fully implemented for all cases, but for a number where it was already interesting. Okay, let me briefly insert an application. Construction of perfect groups. So there is a book by Holt and Pleskin from '89 where they describe the perfect groups of order up to 1 million, with a few orders as exceptions. And I suspect they are exceptions because there's a larger number of groups, and at some point isomorphisms become a pain. To try the cohomology tools, I've used the standard construct group algorithms, which goes back to Besher, Ike, O'Brien, where they used it for solvable groups, and they used PC presentations. And we used that together with Max Horn and Bettina Ike a few years ago to extend the list of groups. I'm using exactly the same thing as in these two papers. It's a different two cohomology. So I construct all modules for the existing groups. I construct compatible pairs. And I reduce the number of isomorphism tests needed by, and that's a generic tool when constructing things combinatorially, to put on some lexicography that I can often discard groups or results if I know I could construct them in another way. So that's the numbers I have so far. This unfortunately didn't finish. I currently have about 1,500 groups. I expect it will be about 2,000 groups. And I hope, unless I run into another trouble with isomorphism in 1 or 2 weeks, I will have this number. Okay. So, going back to our original task, the last thing I need to generalize is PC groups. That they were used to actually represent the cover. Remember, I have to actually do arithmetic in the cover. I have to evaluate the relators in the cover to factor out what would not be compatible with the presentation. So, we anyhow, well, one could, initially I tried to do this as permutation groups, and that gets quite costly. So, what I'm going to do is, again, an approach which has been used before. I'm using the rewriting system I anyhow have for the cohomology, the rewriting system for the factor group. And again, this is in some way already implicit in the book of Holt and Pleskin. They are working with presentations. Jack Schmidt wrote this, mentions this as representing such groups, and there is a paper by Sinanan and Holt where they actually do it in a more general context to describe groups, polycyclic by finite groups. What I do is I write extensions as pairs of elements, factor group, normal subgroup, and I use the rewriting rules where the tails describe me how things change to describe such an extension. and I get a collection process, and that's basically the same as with PC groups. I've implemented this. I use it not just to represent the non-split extensions, but I can also use it for the split part. If I take trivial tails and a prescribed action, I can get a semi-direct product. Subgroups which surject on the same quotient are obtained by modifying tails. Subdirect products are easy, quotients are easy, and that is all I need. I have formed semi-direct products, subgroups of them, subdirect products. That gives me the cover, and I want a quotient of the cover. All of the rewriting currently is done in the library. It's not super fast. If H has a radical itself, I can rebuild and move this, make the solvable part larger, which makes it faster. Well, so far very little else is implemented, and therefore to be able to iterate the calculations, I actually still need a permutation representation of the quotient. That takes most of the time, but I hope that this is something I will be soon able to throw out. So, yeah, the permutation representation, maybe I'll skip about this, how I get the permutation representation. So, what is the quotient algorithm? I start with a finitely presented group, given as a quotient of a free group, fixed rank. I assume I have a first quotient for some group H. Well, here I say fitting free. It doesn't have to be, but I don't need more. Now I iterate. I choose a prime. I take the existing quotient. I classify the irreducible modules. That's basically Burnside-Brouwer, what I'm doing. I start with a faithful module, for example, the permutation module. I tensor and meet X and tensor, and Burnside-Brouwer tells me this gives me all irreducible modules. If I iterate, I construct for each irreducible module the cover. I evaluate the relators in the cover. I take the quotient, and that will be the largest V homogeneous semi-simple, the largest extension with a V homogeneous semi-simple module. Well, and then I take the subdirect product of all of these. This alpha will be the next homomorphism. Yeah, I should have shown that picture earlier. Okay, yeah, right. So this is implemented. There is concrete code there. If you want to run it, currently it needs the development version of GAP. It does not run with 4.10 because it uses some tools. Okay, let's look at some example. The first one, and there in some way you will easily say, I don't really need the algorithm, but that's a known result. I'm taking the Heineken group, which is, well, if you search for Heineken group, you find all kinds of beer worldwide. This is a group defined by Hermann Heineken to look at certain abstract properties of presentations. So that's the presentation. It is not, and I calculate quotients to A5. There is just one of them, though I don't tell you that there is just one, but here you don't see it, but I tell you there is just one of them. And now I'm running the algorithm for prime 2. Well, the reason why I don't need it here, A5 is small. The kernel has only index 60. And there I could rewrite to the kernel. The problem with rewriting is that it increases the number of generators proportional to the index. So for 60 it works. For 60,000 it might not work any longer. Anyhow, A5 has 3 modules in characteristic, irreducible modules in characteristic 2. The trivial one, it extends somehow. This module extends somehow, so it always constructs the covers. It extends, this one does not extend, and I get a larger quotient. The whole thing took 0.3 seconds. And now that gave, so this gave me a 2 cross 2 to the 4, both modules once. If I iterate again, I only get the trivial module. And if I iterate further, I find finally the largest known finite quotient of the Heineken group. Going up to here is 4 seconds, 30 seconds. Yeah, it takes somehow longer. And really, this permutation representation is what slows it down. I just didn't get to throw it completely out. I get, in the end, this quotient in about 1 gigabyte of memory in permutation degree 15,360. Let me do another example, which I hope is a little bit more impressive. So I take a group with a presentation r cubed, s to the 7, r s to the 10, commutator of r s to the 10. This group is known to be infinite, and this is an example of Coxeter type presentations. These groups have been studied quite a bit, both from theory and also as examples for algorithms. I calculate quotients to A10. It finds 3 quotients to A10. Well, A10 is so large that it is not feasible to rewrite to the kernel. So here really is no alternative way of doing this. I calculate the irreducible modules for A10 in characteristic 2. They have these dimensions. For time reasons, I only look at these 2 small dimensions, 1 and 8. If I take the first quotient, I lift only for dimensions 1 and 8. I find that both modules extend the trivial one once, the 8-dimensional 3 times. I get a quotient of degree in the 5,000s. If I take the second quotient, I do the same thing. And that's the reason why I'm doing this. Here something else happens. So if I look at the first and the second quotient, the images are permutations of the same type. In both cases, the first generator is mapped to 3 cycles. The second generator is mapped to a 7 cycle. The product of the generators is mapped to 2 5 cycles. But so that way they look the same. But here I see the first quotient I can put more underneath, namely I can put the trivial one underneath once, the 8-dimensional ones. With the second one, I can't put the trivial one underneath. I can put the 8-dimensional underneath only once. So these are clearly different quotients. So this works in at least approximately practical examples. What are open tasks or things which one might want to know about, which I can't currently answer? Well, I certainly want to avoid the permutation representation. I would like to speed up the collection process with the rewriting systems. This is probably by putting it in the kernel. What would be good primes? Can I find the interesting primes or the interesting modules a priori without having to construct the covers first? There is work by Pleskin and by Herbert Brückner to do this for the solvable quotient. I haven't yet looked at it to see whether it generalizes in some way. Can I do the same thing over Z? Would I want to do it over Z? The representation theory probably will become quite more complicated. Once I have this hybrid representation properly implemented and working, I should use it in other cases. For example, automorphism groups of finite groups. That would be often an obvious way of representing these. Yeah, and that's all what I have. We have a preprint, and there is a URL where you can download the code. Thank you very much. Yeah.
The single biggest obstacle was finding permutation representation of quotients that you mentioned.
That's what I skipped, yes.
We could probably use going up to 1 million, we could probably just use the regular representation.
Yeah.
Those days you couldn't.
Yeah, one could do this.
Are we going to go to more?
Yeah. And the isomorphism. I mean, at that time, I don't think you would have had an isomorphism test, and we're using the Cannon-Holt isomorphism test now, which can do these groups. I mean, I had some numbers in there in between. So this first A10 quotient, it took, I think, 10 hours, and it would cut down to under 20 minutes by ignoring the permutation representation.
There's another question. As a means of calculating two cohomology,
Yeah.
how does that method compare with sort of other sort of methods I use?
Yeah. I haven't really tried, and the problem is a bit that the cohomology code from the, well, it was rewritten in the 90s, I think, but we are getting to a point where it is not always easy to compile it. And that's basically the step I haven't looked at. I mean, in some way, it is less sophisticated in the machinery what it uses. It just uses rewriting. It doesn't do the co-restriction you do. On the other hand, I've tried to implement your 85 paper, and I failed on the co-restriction because there are some subtle things in where you have to ensure that representatives are chosen in the same way again, and that is not completely trivial. Yes. Yes.